Welcome everybody to our second session on day 2 of OptiWave's webinar week. In this presentation, we'll be looking at our OptiMode software package and in particular the FEM solver. My name is Brian Tipper. I'm the VP of Sales and Marketing here at OptiWave, and I'll be sitting alongside your host, Damien Merrick. Before we begin, let's just go over the webinar setup. During the presentation, you're going to see 3 polls. If you are present for all 3 polls, your name will be entered into our $50 gift card draw. The winner of the draw will be announced on our website at noon Eastern Standard Time. We'll also have 2 question and answer periods at the halfway point and at the end of the webinar. As in previous sessions, we're not going to be answering questions via the raised hand option, so please type all questions into the questions section only. Over on the side of your GoToWebinar control panel, you'll notice that we have 1 handout available. Feel free to download this at any time. Finally, we're going to be recording the webinar and distributing it to all registrants via a download link. You're going to receive this link tomorrow at noon Eastern Standard Time. If you'd like to access the recording earlier, you'll need to go to the same link that you used to register for this webinar. And you're going to go ahead and click on the link again and click on the register button again. You'll need to use the same name and email that you used when you originally signed up. It's going to take approximately 30 minutes for the recording to fully render after the webinar ends. So it should be available at 12:30 Eastern Standard Time today. So without further ado, I'd like to hand it over to your presenter, Senior Photonics Application Engineer, Damien Merrick.
All right, thank you, Brian. I'm Damien Merrick, and I will be giving the presentation today on OptiMode, a software package we have that comes with OptiFDTD and also OptiBPM, and it's used for mode solving, so finding the propagating modes and also leaky modes of optical waveguides. In particular, today we're going to look at the finite element method and how it's used to find leaky modes of waveguides, with an application that's to do with anti-resonant reflecting optical waveguides, a paper from literature that I will be reproducing. So let's continue on. Okay, so the structure of today will be starting with just a quick explanation of waveguide modes. I'd like to start everyone off on the same foot before I start talking of things more in depth. And then I'll go over, again, a very broad overview of the finite element method. It's important to understand it a little bit so that you can understand how to use the mesh properly and how to get a better result. If you don't understand it, then I think there'll be some confusion on how to get a proper answer. Then I'll go into detail on our how we employ the absorbing boundary conditions using uniaxial perfectly matched layers. Again, if you want to solve leaky modes of waveguides, you have to have a pretty good understanding of these boundaries and how they work. You might get lucky and just use whatever is default and hopefully get a good result. But if you want to actually use it properly, you should understand what it's doing and how to use them and what the parameters mean. Then we'll move on to the arrow example, and I'll show you the results and how to do it in OptiMode. And then I'll display the convergence results, and if there's time remaining at the end, I'll show some extra content depending on what I think how the presentation is going or where we're going. Okay, so a waveguide is a structure where the light is confined within some core or some guiding structure. And the idea here is that we assume that the material properties or the structure is independent of one direction. Usually, convention says that's the z direction. So in one direction it's uniform. You could say it's translational symmetric. That'd also be correct to say that. And we also assume there's no sources of electromagnetic field present in the structure. So we can then use the sourceless Maxwell equations to describe it as a wave, as only waves propagating along the structure. And we find that if we use a solution where the electromagnetic field is periodic along the propagation distance, It will have a transverse spatial distribution, a complex field, as well as a propagation constant, or you can also describe it with an effective index. We also use here the fact that it's a harmonic field, so we have the omega t here, right, at a certain frequency. And I just wanted to clearly show how, in our mode solver, you'll get the results of the field and you get the effective index. I wanted to show from the equation how this breaks down, right? So on the left here, the field is this xy dependence of the spatial distribution, and from this data you can calculate things like how much the field is confined to the core, the effective area for nonlinear type applications, and the polarization as well, if the field is mostly pointed along x or y. And on the right here, we have, if you designate the frequency or wavelength of your simulation, and then that'll give you the effective index, or if you combine the wavelength into the effective index, you'll get the propagation constant. And that's a number, or an eigenvalue of the problem, and that tells you how this light is propagating down the waveguide. So different modes propagate with different effective indices and different propagation constants. Now the effective index can be complex, so that means the real part will describe how the phase changes over the distance, and the imaginary part will tell you how it attenuates. Usually attenuates. We don't really deal with active materials in the mode solving. And then the attenuation will become a negative part of this effective index. You'll see a negative value to it. And on the right, I'm just showing the cross-section of later what we're going to be simulating. It's the arrow structure, and it's made up of different dopants, different percentages of these semiconductor materials in aluminum arrayed in a structure like this. And the interesting part of this structure is that since the substrate has the same effective, refractive index as the core, it's going to be a leaky mode. Although there's this lower index sort of boundary here in the middle, since the surrounding substrate down here is the same index, you're going to have a leaky wave that'll be leaking out of the core here. And I have the reference down here at the bottom where we got this paper from. Okay, so let's switch gears now to the FEM and sort of describe what's going on with this method and how it's different than the finite difference mode solver. So the main difference is how the simulation domain is discretized, as far as you need to really be aware of. Instead of a mesh, a rectangular mesh or a sampled mesh, as we see in the picture on the right, you'll see that the domain is made up of these little squares or little rectangles, and that's fine, although it does lead to some problems when you're trying to approximate a more complicated structure like a slanted wall here. We see that there's sort of a staircase, and you might think that that's not a big issue, and most of the time it's not really. But if there's a high index contrast, like here we have 3.5 in the core here and then air on the outside, it's like a silicon exposed to air. Very minor changes in the effective index, in the refractive index, can change the solution. So the finite element mesh uses a triangular mesh, and that approximates this diagonal slanted wall here a lot better. And now I'll switch to the software, and I'll show you how that works when I can find out where that window is. So this is one of our basic examples just to show that structure. So here we have the structure over that slide, and the core here is in red, the high index. We can click this button up here to preview the mesh, and very quickly we can see the mesh overlaid the refractive index sampled result, and you see that this line here is representing that boundary, and it's much closer to the actual wall than the sampled rectangular mesh. Once all these settings are set up, you would just go to solving and then solve the FEM. I'll talk about these in a little bit, but for example, this is controlling the mesh here, right? The triangles will have a minimum angle of 15 degrees. the minimum edge length is 0.01 microns, and the edge length of the triangles will be at maximum 0.06 microns. So we can run this. We're looking at one mode here. And you'll notice here it's displaying the permittivity as a tensor. There's XX components, and it's a transverse anisotropic type material, the longitudinal part. So we can see the field here when it's solved. It gives this type of distribution. Let's return now to the presentation section. So the next thing I want to explain is how do you approximate a field with the finite element mesh, and what that means is not what that means. I mean, how does that mean you should get a better approximation? What choices you should make to get a better result? So, as we said, we approximate the domain as this mesh of triangles, and then over each of these triangles, here we have an example of one that's isolated. We use these polynomial basis functions. So, for the first order example, we have one here where we have the field as a constant tangential to edge 1. It's hard to see because the arrows also have a normal component, but if you isolated the tangential part, it will be constant along this edge 1, and then as it goes to the opposite node over here, it goes to 0. And then for this element, you'd have 3 of these basis functions, and then using them, you can add them up with different weightings and to get a pretty good approximation of the field. And the idea of the finite element method is to choose values of the weightings of these functions to get the best approximation of the field. And you want to minimize the error for that approximated field. So how would you improve accuracy of your solution? You would, for example, you might decide to use smaller elements, right? If you use a smaller element, then the field will be a linear approximation will be a better approximation for that field, especially where the field is changing rapidly. If you don't want to use smaller elements, you also have the choice to use higher order elements. This means instead of using a linear approximation, you would use a cubic or a quadratic. That means the field will be, the basis functions will be actually a function of a quadratic order or a cubic order. And I think I have an example of what a higher order basis function looks like. And here's one. It is, I believe, a quadratic basis function. It has another sort of 0 node on the top edge over here. However, it does decay to 0 at the opposite node. This is the basis function associated with this edge at the top left. So that's important. The 2 ways to improve accuracy is using smaller elements or using higher order elements. Personally, through a lot of my own practice and going through literature, I've found that using cubic order elements is a very good starting point. It provides a high level of accuracy. So I showed this same type slide in the FDTD introduction, where I explained the boundary conditions that use an FDTD and also in the mode solver. 2 of the main boundaries conditions there are perfect electric conductor and the perfect magnetic conductor. Right, the perfect electric conductor forces the tangential electric field to 0, and the perfect magnetic conductor forces the tangential magnetic field to 0. Going on, I'm not going to talk about that too much, and I'll just say that in a lot of cases, the best choice to start off with is that perfect electric conductor. Right, if your boundaries are far enough from the core that the field is decaying to 0, then that choice is perfectly fine. And it's the simplest choice, in fact. However, if your core, or if you're expecting your waveguide structure to have a leaky mode, as we are expecting in this presentation, you'll want to use absorbing boundary conditions, which are employed via the uniaxial perfectly matched layers. And I'll talk about that on the next slide in greater detail. And then there's also the choice of using a symmetric boundary condition. If your geometry is symmetric along X and Y, X or Y, you can choose to use a boundary condition that will exploit that symmetry and split the domain in half and create a much faster, results in a lot faster simulation. So let's talk briefly about the UPMLs, because I think it's important to understand what those parameters mean in the OptiMode parameter box and how to use them. The idea here is that you have your domain of interest, I called it, and the gray here. This is where your structure actually exists and what you're trying to model. And then on the outside, you'll have a boundary layer that will be used to employ the UPML materials. So this is sort of like a padding layer between the domain of interest and the hard electric wall boundary. The UPMLs, although are a different boundary condition, at the end of the day, they do actually just enforce a electric wall on the edges after the PML region. And what they sort of do and how they're used is there's different ways of thinking about it. You can think about it as modifying the Maxwell equations to allow a field to decay. You can think about it as modifying the space so the field is actually traveling through a complex space. It's kind of interesting to think about it that way. But the best way, I think, for possibly engineers is that it's just a fictitious material that we can make theoretically that offers very low reflection. In fact, theoretically should be zero reflection between the domain of interest and the absorbing material. And also any waves that travel through this material will experience an absorption or attenuation. So a wave that's traveling to the right in this domain will interact with this interface, should reflect not at all, travel through this boundary layer, hit the hard electric conductor wall, and then reflect. However, during that time, it has to travel twice through this layer, and that will result in a high absorption. So the way to engineer this material is you take the electric permittivity and the magnetic permeability, and then you modify it sort of in a symmetric way. If we modify the permittivity and permeability in the same way, the impedance of the material will not change. That's why a wave will not be reflected by the interface. Just like a transmission line, if the impedance doesn't change and there's no reflection, in this type of simulation, the wave, a plane wave or any type of wave, will not be reflected either. And we modify the components of a tensor using these values, which are called the S parameters. And they're given by some complex number, which has this conductivity up here, and also the frequency. This column just normalizes it to frequency so that different frequencies get absorbed at different rates. And that's the basic idea here. We're just increasing the imaginary part of the permittivity for certain components and dividing by it for others. Now, theoretically, like I said, these interfaces should not reflect at all. However, in practice and when you discretize a domain, there can be some reflection because of numeric error. So what is done usually is that instead of just turning on this high conductance, high absorption material right at the interface, we ramp it up. So right at the interface, it's zero. The material doesn't change at all. And then as a function of d, which is your position within the material, divided by the thickness of the material. So this is sort of like a normalization, which this will go from 0 to 1. You can use a order here, like 1 or 2. You can square it to get a different type of polynomial function. It'll ramp up from 0 to some sigma max, right? So that's important when we're going to be setting up the simulation parameters in our simulation. And then the different layers here will have different settings for those S parameters, right? In this region, SY and SZ are set to 1, and SX is the one that will have this non-1 value or imaginary value. It'll be totally complex, but it'll have a larger imaginary part. That's to absorb waves traveling in the X direction. And the sort of the Y boundaries, SX and SZ are set to 1, SY is set to this value calculated over here. In the corner regions, since you might have waves traveling a combination of x and y, you have both x and sy set to non-1, but sz is always set to 1. And now I just have a quick plot of what I've included the sort of fictitious materials in this plot, and we can see how it ramps up slowly. So this is actually the aerial waveguide, and I've taken just one component here, the epsilon xx of the tensor, and we see here that in the vertical slice, so this is the core area, and I'll also use symmetric boundary conditions, so you can see this as it's mirrored from the left to the right, but it's symmetric along this vertical axis. You see that it's normal in the simulation domain, and then about here we start turning on the absorbing boundary conditions. It starts to ramp up. This is the absolute value, so we don't see, it's not the imaginary or real, but it's the absolute value of the permittivity. And this starts to ramp up. However, in the horizontal direction, we see that it ramps down because it's actually dividing by sy for the exx component. Or yes. Well, yeah, sorry. Yes, exx is either being multiplied by sy if it's down here, or divided by sx if it's going over in this boundary. So there's a different behavior. But I just want to show clearly how that material is being ramped up to a higher value, an absorbing value. So I think now is a good point to have this poll started. Brian would like to ask you a question, and while that's happening, I'll read some of the questions I'm getting in the question box and reply to some of them. And at the end of the webinar, I'll try to reply to more. So take it away, Brian.
Okay, so we're going to just launch the second poll here for you guys. So again, we launch these polls and ask you guys these questions just so we can understand exactly our audience and determine what is best to show you guys in these sessions and kind of guide the session a little bit more towards the audience that's actually attending. And just to go over, if there's any questions about pricing or whatnot, please just send us a direct email to info@optiwave.com. We can take care of pricing directly or setting you up with the appropriate sales channel so that you can get that information. And also the additional sessions are always available to register on our website. So the page that you originally registered has quite a bit of information on it. You'll have all the additional webinar sessions up there. You can click on the sessions that have gone by, and if you click on register again for that session, you'll be taken to the recording, the video recording of that session. And also you'll have the names of the $50 gift card winners posted there, along with the approved entries into the draw. So again, to be approved for the draw, you have to attend the entire session, which we basically look at as you being in the session for all 3 polls. Okay, I'm going to close down this poll and pass it back to Damien.
All right, thank you, Brian. So I see 2 questions here that I'll answer. There's some other ones, but these are the 2 sort of more important ones I think that I'll address. So one of them is, can we model silicon-based optical devices besides gallium arsenide, i.e. 3-5 group-based devices? And the answer is, I believe yes, because we can model the optical portion of any of these devices, right? Of any type of waveguide. That means that we're modeling, you give it a refractive index, a permittivity, could be complex, it could be anisotropic, it could be absorbing, and then we will tell you the results of that material and how that affects a wave traveling through it, or the modes that will travel through that type of refractive index material. However, we won't tell you how to calculate the band gap of such a semiconductor, right? This is an optical simulator. It's not going to simulate electrical band gaps in the semiconductor. Another question here says that the FEM assumes no sources of electromagnetic field present. Does that mean no external field, like an excitation pulse, for example? It's it doesn't mean that it's not modeling a waveguide being excited. It's just saying that if you excite a waveguide, say at z equals 0, maybe it's a very bad excitation. You just send in like a really not a clean source, like a point source that's just going to sort of vibrate the field in any direction. If you look really far away at z equals, approximating infinity, the modes, the field you're going to see, if the waveguide is a fundamental mode, the wave that you're going to see is going to be the fundamental mode, and that wave will be propagating with that associated propagation constant, right? So if you excite it with any source, you're going to excite the propagating modes, and you also excite the radiating modes, and these radiating modes will radiate the wave away from the waveguide in a very short distance. But if you look down range, sort of, or at a far distance, the field's going to take on properties of the fundamental mode. And since a lot of waveguides, especially in fiber optics, are very long compared to the wavelength, usually it's a very good approximation, right? Optical fiber can be kilometers long easily, and that's many, many, many orders higher than the wavelength. So these simulations give you an idea of how light propagates in these waveguides, sort of regardless of the source at a long distance. But that's a good question. All right, I'm going to continue on now, and I'll show you the example that I have set up. Not this one, we already showed this one, but this one. Okay, so I'll show the refractive index distribution again. There's some slight subtle differences between the refractive index. There's the blue here, which is air, so it's got a very low value compared to the other ones. But those layers have a very similar refractive index, right? In the middle here, the core is 3.59, and the slightly off red color here is a little bit oranger, and it's 3.452. And there's also another layer down here that you probably can't even pick up on this webcast because the color is so close, but it's also slightly off. It's 3.555. And then down here, it's the same refractive index of the core, which is why this mode will want to leak out into the substrate, even though there's some type of barrier between it and the substrate. Now, like I pointed out in the beginning, this geometry has a symmetry down the middle, right? The left and right are equal if you slice down the middle. And so we can actually half the simulation time if we only care about this right side of it. If you look at the paper, or if you go do some simulations, you'll also find out that the fundamental mode here, or the fundamental mode is X polarized. So we want the major component to be X, which is pointing left and right, which means we want to use an electric wall boundary condition. You see here I've set, this is the solver settings of the FEM mode solver. I've got min X is symmetric electric wall, which means it's going to put a boundary right in the middle, and it'll enforce an electric wall. So the EY component will be forced to 0 here, but we want the mode that has the major EX component polarized in the X direction. At the maximum X on this side, I've got absorbing boundary conditions. It's not very needed, or might be slightly needed, because the wave's going to be mostly leaking downwards. It's going to be hard for it to come out over here. And the top I have electric wall, because it's actually going to be very confined to the core here, so it'll decay very quickly to 0 at this boundary, so electric wall is fine. And then at the bottom, importantly, I've chosen the absorbing again down here. Now I can preview the mesh. Before I actually run the simulation, it's possible to see how that mesh superimposes over the structure. This gets you an idea of how the resolution of your triangle mesh, right? You'll notice that it's only meshing half the structure because I've used that symmetric boundary condition. Also, I've got absorbing on the X, I've got absorbing on the Y, which means that's the reason why it has this added layer here. It's about a micron thick. It's a pretty large absorbing boundary. And down the box down here, it'll explain some of the properties of this mesh. The most important one is the degrees of freedom. Also, number of elements. But this gives you sort of a relationship between your simulation and how much memory and how long it'll take, usually. If you're looking for like 100 modes, obviously your simulation time will be longer than if you're looking for maybe 2 modes. All right. So once you're sort of happy with the mesh, you can then solve it, like I showed before. And then I'll explain these in a little more detail as well. I explained the maximum triangle area before. This tells the mesh to create a mesh where the triangles have a maximum size of 0.02. So if you want a more refined mesh, you'd make this value smaller. I've also decided to use cubic elements, like I explained in the slideshow. This will give a very good and accurate result. I also have this initial estimate box up here chosen to look for modes near 3.574. Now, if you don't know what mode the effective index is going to be, you can just use the max index. This is usually a pretty good choice. In some types of waveguides, it's not, like a plasmon polariton type waveguide. However, in this one, I have the results from the paper as well as previous simulations I've run, so I can use this. I already know it's going to be around this answer, and that'll help it converge a lot faster. Yeah, so I can run it now. This one has a pretty fine mesh. I fine-tuned it to give an accurate answer. So it takes some time to set up the mesh. Once it's got the matrix created, it'll start stepping through the eigenvalue solver. This one should terminate at about 100, 101, I think. And then we'll see this fundamental mode that's reported in the paper. While this is going, I'll also just show you the parameters for the absorbing boundary, right? So we've set absorbing boundaries on the y and the x. This is the thickness of it, right? This is the thickness of the layer. A larger thickness usually results in a more absorbing layer. This is the order of the grading polynomial. I showed you that function of how you can increase the conductivity profile. This is related to what order you want to use. And then this is the sigma max x and sigma max y. So if you choose a really high value, you might get some numeric error and get a wrong type result. If you use too low, you won't actually absorb all the wave traveling, and you won't also get an accurate answer. And I'll show this back in the slideshow in a second. But this sigma x and sigma y is related to the equations I showed at that slide, that max value. It should be done now. So I found 2 modes. The first one is a fundamental mode. You'll see that it's polarized in the x direction, right? The major component is EX, and the EY is much smaller. And now if you're present for the OptiFDTD introduction, I talked a lot about how to investigate the phase and see what that means about the simulation. Well, if you look at the phase here, we see that it's decreasing in the negative y direction, right? It's pretty constant in the core here, and I'll just explain this kind of speckled pattern up here. The speckled pattern is because the field is so small that it's giving a sort of error on the calculation. It's jumping between 0 pi and negative pi. But it's just because the imaginary and real parts of the field are so tiny that the function is just giving a weird result. It's not very important. If we look at the phase down here, though, we can see that it's decreasing, and I can show it's decreasing almost linearly. If I take a plot here, if I take a cut right down the center, right down the center here, we see that in this section the phase is decreasing almost perfectly linearly. And this tells you, like I explained in the FDTD introduction, that it's like a plane wave is traveling downwards, right? So that's the leaky part of the mode. The mode has a propagation constant, which is actually a vector. Usually it's pointed directly along z, but in this case it has a component that's going downwards in the negative y direction. And so you can clearly see this wave traveling downwards with this cut. You also see that some of it's sort of it's kind of spreading out once it gets into the substrate. And that makes sense because it's free to move to the right or downwards as well. Yeah, so that's how you set up a leaky mode simulation. I'll switch right back to the PowerPoint right here just to explain an important aspect of it. So, like I said, you need to sort of understand how the PMLs work, and you should always do a convergence test when you're using them. Always start with what I call, or what are called, sort of the hard boundary conditions. That's the electric wall and the magnetic wall boundaries, because they're the simplest to use, and even though they might give wrong answers for a leaky mode, they'll give you a good approximation of what type of modes you should see. So you might, like you could do this simulation with hard metallic boundary conditions, and you'll see that the fundamental mode is X-polarized, right, for example, and you'll get roughly the correct phase constant. So that's a good starting point. And then you can start using PMLs and start increasing their absorption properties and see how that converges to a result. So this is similar to in the paper that I took this example from. I'll show the references at the end of the slideshow. You start off with a very low sigma max. Right? This is what this is plotting. I plot sigma max x and y and how that affects the phase constant. So this is the real part of the effective index, or real part of the propagation constant, and then the imaginary part, or how the field is attenuated. So for a 0, there's no absorption, so obviously the attenuation constant is very close to 0, or it is 0 in fact, and the phase constant has some value that is probably incorrect. And now as we run simulations while increasing the sigma max, we see that it starts to converge to a certain value, and this value is very, very similar to the one in the paper, which is great to show that it's true. Just down here, that the attenuation has a slightly different behavior. It sort of overshoots, but after a while, it does converge to the result. And I think if you're ever doing a leaky mode type simulation, you should always do it like this. You should always start off getting an idea how the waveguide works, and then move on to doing a sort of a convergence analysis of the phase constant and the attenuation constant. So that was the arrow structure. We have some time here, and I want to talk about another thing that's important when using the finite element mode solver. And I'll switch back. It's going to be to deal with the grid points. And I'll switch back to the software here, and I'll open up that first example again. So you'll notice that in the FEM solver, there's this grid points down here. This doesn't really affect the accuracy of the mode solving, because the mode solving uses a triangular mesh, which are set up here. However, all our displays and plotting utilities always have a rectangular mesh. So if you want to actually see the field, then you actually have to revert to your rectangular mesh and sample the field values at different x and y coordinates. So you might have noticed that in my, I think I can, let me quickly just open up the previous result I had. Where is it now? You'll notice that even in the finite element approach, there's still, the field looks sort of like a staircase, right? And I promised you that that wasn't happening with the finite element method. However, since we're sampling it on a grid, we're getting this behavior. If you want a higher resolution image, we can always change this to a higher value. It'll increase the post-processing time slightly, but it won't change the solving time. It'll just increase sort of the last stage where it calculates the field. But you should get a better resolution the final stage. It didn't change much, but it would have been probably easier if I had gone the other way and used a more rough grid point. But that's just to show the fact that the field is actually accurately calculated at these scientific walls. This is just an artifact of our kind of display, how we display the field. Okay. And before I move on to questions, I'll just mention something else because there's a bit more time. Right, so there's different meshing techniques we can use with the finite element method. It's got a very, it's a lot more easy to use. It's a lot easier to enforce a different mesh on a find element method than a rectangular FD method. So here, for example, it's very subtle, but we can have a material dependent mesh. So if we look at the triangles in the red portion, which has the high effective index, which usually means the field can be changing more rapidly, it has a smaller triangle size. And in the air surrounding this core, we have larger triangles, right? And we can also do a from file mesh. If I switch back to my desktop, I'll solve this again, but I'll set it to 300. If you already have a solution to the problem, you have a field distribution, you can use that previous solution to get a better mesh that will solve that mode. So I want to quickly show it. So I'm just going to export this mode really quickly. So I'm exporting all the field values here into a file. And then if I go back to this one, the designer, and I change the advanced mesh settings such that it's using a from file type, I can designate a file to use. I want to make sure that the EX is the major component. I don't remember. Yeah. So I'll use the EX component as the starting mesh. And I'll change some options here. So now this max triangle area is going to depend on the gradient of that solution we had from the previous simulation. All right, it's not quite as fine yet. I'll just increase the resolution a little bit, make the triangle smaller. But you'll see now the mesh is sort of adapted to the answer that it should be, and we're getting a smaller mesh where the field is changing most rapidly. You'll see at the middle they're larger. That's because this mode has a flat sort of top in the middle, so the derivative is very low. The gradient's very small. So we don't need a lot of triangles for that flat part. But near the interface where the field is changing the most, we have smaller triangles where it's needed. That's an interesting thing you can use with a finite element mode solver. Okay, I'll take this time now to read some of the questions that you have, and I'll allow Brian to continue with the third and final poll. So Brian, take it away.
Okay, so the last poll should be up for everybody. Please take a second, answer it quickly, and then Damien will try to get to your questions. There are a couple questions that came in, and of course, they're all very technical, couple sentences long, so then it'll take a bit to read through them. But just to let you guys know as well, in the afternoon today, we have our OptiSystem basic examples and analysis at 1 p.m. Eastern Standard Time, and at 3 p.m. we have the second part of FDTD, the basic examples and analysis that will be done at that time. So definitely feel free, if you're available, to attend those, and you're interested in the content of those webinars. We'd love to see everybody come for those as well. So I'll go ahead and pass it back to Damien. Hopefully he's had a second to read through a couple of those questions.
Yep, I read a couple of them. Some of them are not really appropriate for this type of format because I would need to respond to them in more detail. But one question is sort of, how can you figure out which modes are excited from an excitation field? And we do have, in our OptiTools software, or utility that comes with it, we have an overlap integral. So you could choose some excitation field and then overlap with the modes of a waveguide that you've exported. So you could find out how the excitation takes place that way. So yes. And another one is that's a good question. How do I do that convergence analysis? And the answer is there's things that you can script in OptiMode. However, when we set up this one right here where I was changing sigma x and sigma y, that has to be done from a different method. You can't quite use the scripting from the software. You can make multiple, it's a little more complicated than that. This is something that's a good feedback though. We should probably allow behavior to do the sigma x convergence. You can use scripting to increase the number of points in mesh. So you can do convergence analysis with a finite difference mode solver quite easily by increasing that. It's a good question. Okay. So I think that is the end of the questions that I would like to answer at this time. So please, thanks for listening in, and hopefully you're going to be around for the next presentation at 1. And I'll see you then. I'll be around for that presentation. So thanks again, and see you.
Thanks, everybody. Have a good day.